So our third talk for the morning is Mario Carneiro, wizard in residence for the Lean community, and a postdoc. Oh, you're at Carnegie Mellon.
That's a lie.
Okay.
That needs to be updated. That should say
a postdoc at Chalmers University in Sweden.
That's correct. Yeah.
All right. Telling us about sort of going deeper into the system. It's turtles all the way down, as they say, and that's what Mario will explain to us.
Yes. So, thank you all for coming. So this is maybe going to be a bit of a crunchy subject. So I'm going to try to keep things at a sort of middle level of complexity here. But I also I hope that you can sort of come away with some understanding of actually what Lean's meta theory is. And I'm also going to tell you about some projects related to this topic that I've been working on recently. So I don't think I need to explain what Lean is to the people here. I think that, so far, I think all of the previous talks have been about Lean. So you probably know by this point what it is, but what's relevant for this talk is that Lean is an ITP, and it's based on dependent type theory. And specifically, it's an extension of Martin-Löf's type theory called the calculus of inductive constructions. So ITPs are usually presented as a sort of alternative or supplement to informal proof. And writing formal proofs is complicated and slow, so why do we do it? And I think many people can give answers to this question, but besides the one like it's fun or we enjoy it, at least one of the reasons that we'll write in our papers that this is why we do it. Is that well, if it's in the computer, then you can be sure that it's correct. All the stuff we did before, not so correct. Now we got it right. Well, okay. Why is it that we should, believe this statement, right? Formal methods tools in general are usually held to a higher standard of correctness than most software. This is in part because formal methods are used as sort of backup validation for other tools which are maybe more efficient and reckless, right? They try lots of things. They maybe have more bugs, and so when you have difficulties with that, you fall back on some system that is sort of foundational and is checking things in a more rigorous way. And even among formal methods tools, there's a sort of hierarchy of more and less trust, and ITPs are usually up there, whereas SAT solvers and SMT solvers tend to be on the sort of more complicated and reckless, and the model checkers where you're sort of checking most of a proof, and that's sort of, and then I guess testing would be the next level beyond this, right, where you're sort of trying to make sure that things are all right, but you're not really, doing a formal proof. Now, there's a sort of tension in the specification of an ITP. So ITPs should be very secure, sort of even against adversarial usage, so that we don't have to look too closely when it claims a proof is true. Why do I say adversarial usage? Well, we now have tools that really like to find proofs of false. And ITPs should also be convenient to use. It should come with a huge and extensible list of proof methods or tactics, and they should empower users to write proofs in the most natural way for their domain. And these two are really in direct conflict. So this number 2 here says that a good ITP should be complicated, but that increases sort of the risks when you're trying to defend against possibility of unsoundness. And they can even be conflicting by design. So if this is empowering people enough that you're literally giving them the tools to exploit the system. So in order to address this, most ITPs, including Lean, solve this conundrum using the de Bruijn principle. So this says that a program should have a small trusted kernel, which is responsible for checking the theorem. And so this allows most of the system to have a sort of lower standard of correctness. And then this kernel is, it can be audited for correctness. And so you can see this in just numbers, right? So if you look at it, if I just go to the Lean 4 source code, I just count up how big is the source directory, all of the files in it, just count it off. I get 493,000 lines of code. That's a lot of code. And then you compare it to what's in the kernel, and we're only at 8,000 lines of code. I think that's still a lot of code, but it's less code than the whole thing. So what is the kernel doing with all of that code? Well, it's implementing the rules of type theory. So what's type theory? So I am going to go really quickly through this. So type theory is usually presented with stuff like this, and I'm just going to tell you a little bit about how you can read this. So we have these bars here. These are called inference rules, right? So the things at the top are the things you're allowed to assume, and then the things at the bottom are what you deduce from that. And at the top, we have sort of the definition of expression. So an expression can be a variable, a constant, an application. This lambda thing here is called a lambda. This for all is also known as a pi type. And UN, you'll usually see this written as sort U or type U in Lean. These are universes. And then gamma, for some reason, is the letter we use to write contexts. And so that's the thing that you'd see sort of above the turnstile in the Lean goal view, for instance. And so these are rules about how you type an expression. That is to say, here we have like in a context, an expression has a type. So we read this as like, this is the expression that we're trying to type check. This is the type that we're asserting that it has. And then we can deduce that from previous fact. Okay. The two major concepts that we actually need in order to type check are these two mechanisms. One of them is that a term has type, and the other one is this one here, which says that two expressions or two types are definitionally equal. And so this is a sort of congruence on expressions that tells you that two types should be treated equivalently. And when they can be treated equivalently, then when you have a term of one type, then it's also of the other type. Okay, so Lean-specific flavor of dependent type theory has an impredicative universe, propositions, definitional proof of relevance, no universe cumulativity, index, mutual, and nested inductive types, and an eta reduction rule for lambdas and structures. I'm going to explain what very few of these things mean, but hopefully you'll come away with something. So inductive types are basically, we want sort of a general framework for being able to define types which are generated from some data and have sort of no more than that. I'm giving here just sort of a minimal description of how you can describe what an inductive type specification is, but just sort of demonstrate like the power of like being able to define types in this way. You can construct NAT. So NAT is an inductive type which is generated by zero and successor. So here we have we say that it's sort of the least type T, such that zero is in T and successor is a function from T to T. You can also define non-recursive inductive types. So like here, this is the definition of exists, where we say that it has sort of this argument x of type alpha, and then a proof of p of x, and then you get an element of t. So the least thing generated by this is exists. And you can define a lot of the propositional connectives in this way. So each inductive type comes with a constructor. These are sort of built into this picture here. You see these zero and successor. Those are going to be our constructors. So we get those. And then we also get this complicated thing called the recursor. And that's sort of how you do induction over an expression. And it's how you build definitions by recursion. Recursor applied to the constructors. So you can basically say like, okay, I have a recursive function which when applied to zero gives me this element z, and when applied to the successor you apply this function s that I give you on the value at the lower level. So you can use this in order to define a function by recursion. And there are some more things that you can do with this. You can have inductive families. This now allows you to define things like equality. So equality is actually not a built-in. It is an inductive type in Lean. You can actually define it using this sort of mega schema of how do you construct all of the inductive types, right? And so there are these rules about how you can't define you can't just write down anything here because there are some inductive types which, if they existed, the system would be inconsistent. This is an example of a type which, if it were allowed to exist, it would violate Cantor's theorem. And you can prove Cantor's theorem, so that's a problem. Another thing is we want to sort of treat all proofs of a proposition as the same, and that is sort of formally cashed out as this property here, where we say if we have two, so P is a proposition, and then H is a proof of P, and H prime is also a proof of P. And so if you have two proofs of P, then H and H prime are definitionally equal. So this is a rather strong property, and it says that we really can't have any structure going on. This is anti-hot. This is it disproves the univalence axiom. There are also some conditions on when you can eliminate into other universes. I won't go into details on that. And then there are three things in Lean which actually have the axiom keyword next to them. So most of the stuff that I described just now were built-in inference rules of this system. They don't actually come with axioms. They're really just built. When you write down a pi, there's nowhere where pi is defined in the library. It's just sort of already there. Whereas these guys, you just stick them in the system and say they're axioms. So one of them is propositional extensionality. So it says that if you have two propositions and you can prove one from the other, then they're equal. Quotient types. So these are defined as axioms, but this is a little bit of extra magic that the kernel has to be aware of these definitions so that it can say that this holds as a definitional equality. And then the axiom of choice, which is stated here in a relatively simple form. This is a quite strong version of the axiom of choice, where we say we have a single global choice function over the whole universe. Okay. So there is a sort of obvious model. So if you, like me, have difficulty thinking in type theory without being able to connect it back to set theory or something that you understand better, then it's nice to know that you can take type theory and embed it in a very direct way in set theory. And so we can say that when we have when we have a term in some context, we can interpret it into a set. And we have some interpretation for the context. And we'll interpret the type of propositions to a two-element set. So it's got true and false. And the elements of those sets are respectively empty and a one-element set, because true has one proof, and because of proof relevance has exactly one proof, and false has no proofs. So makes sense. And then we can interpret functions as functions. So when you have a pi type, this is a sort of dependent function. So that means that depending on what the input is, you'll get different outputs. But we can write that down in set theory as well. And so, yeah, we can just map pi types to that. Universes are where things start to get big, because universes need to be closed under a lot of operations. And so the rules of type theory basically say that these have to be Grothendieck universes. And so we can take, if we have the nth inaccessible cardinal, then we can define the levels of the cumulative hierarchy to be our universes. And then that gives us a model. And so this gives you sort of consistency proof for lean that if you have this interpretation function, then you get these properties that, okay, if you have a typing relation, then an elementhood relation holds. And so in particular, if this was false and this was some proof of false, then this would be an element of empty. And since that can't happen, then you know that there are no proofs of false, assuming that this, setup exists. And so you can basically turn this into a relative consistency argument that says that the lean, well, this is 1/2 of the proof of lean's equiconsistency with ZFC. So this is a slightly complicated axiom system here. We're going to say ZFC, and then there are 2 inaccessibles, and there are 3 inaccessibles, and there are 4 inaccessibles, and so on. So I'm going to give you an infinite family of axioms that say there are n inaccessibles for each n, but I'm not going to give you all of them at once. And that's because lean can only talk about a finite sort of piece of its type hierarchy at a given point. Okay. So I'm going to tell you now about 2 different projects that I've been working on related to lean meta theory. Lean for lean and a project that I'm calling reverse lean, which none of you have heard of because I have named it last night. So first I'm going to tell you about this one here, so lean for lean. So most of the section previously was worked out in my master's thesis informally about 5 years ago. It's been a while since then, and we have a new version now. So actually the theory has actually changed a little bit. It did make some kernel changes. And Lean 4 has had some minor short-lived soundness bugs. But like me seeing this is like, maybe it would be time to you know, shore this up a little bit. So just to give a bit of context here, Lean is about 80% written in Lean. That includes the parser, the elaborator, the tactic language, the metaprogramming framework, and the LSP server. The exceptions are, well, the runtime. This is a very small piece of the system that's needed in order to actually run Lean code, and it's written in C. The interpreter, which I guess it has to be there for sort of efficiency reasons, and some legacy code, and the kernel. So I think that, you know, one of these is mathematically interesting and soundness critical, so maybe we should do something about it. So the project goals for Lean are basically to create a Lean kernel that is complete for everything that the original can handle, and competitive with the original, so that it can actually be seriously considered as a replacement. I would like to have Lean for Lean replace the existing Lean kernel. The second part of this project is to sort of write down the type theory of Lean, the material that I was describing earlier, but formally this time, in Lean itself, and to prove some structural properties about the type system. And then the third part is to prove the correctness of that implementation, this Lean kernel, with respect to this specification of how does Lean work. Question?
Can I suggest the fourth goal, which is to improve diagnostic transparency into the kernel's operations?
That is an excellent point. So I will get at that in a bit. That's not directly a project goal, but it is an outcome of this project. So just to summarize the progress on this, so there is now a Lean kernel, and it is complete and it is competitive. The type theory of Lean has been written, and some of the structural properties have been proved.
You formalized your thesis.
I have formalized parts of my thesis, yes.
And updated.
The updates have been written down. There are still many sorries. I'll describe more on exactly what the progress is. And then also, this is actually new. This used to be an X, but now it's in progress. Prove the correctness of the implementation. Here the idea is we want to actually define the specification of the individual kernel functions and what do they do, and I'll show you some stuff there. Okay, so the Lean kernel is basically a carbon copy of the C++ code. So it was originally written in C++, and I sort of copied that code over, rewrote it into sort of functional style, and tried to avoid using like IO and other things that I know I won't be able to prove properties about. Just use the things so that I can have a theorem at the end, right? And it uses all of the tricks. It's got union find, it's got pointer equality testing, it's got bidirectional type checking, whatever, all of these things. It has a naive implementation of substitution and reduction because the original also does. There's a sort of tension here where I actually want to make changes to some of these things. Like the kernel in some ways is just not good. And I don't want to actually change it because, well, in the original lean kernel, there are concerns about like introducing soundness bugs as a result of adding optimizations and so on, which is a perfectly valid thing. And so part of the idea here is that by having something with formal guarantees, we're going to feel much freer about being able to just make changes when we, want to make it go faster. And I think that actually we will be able to beat, there was some performance concerns. Well, I guess I'll get on the next slide, but there are some performance concerns, but I think we can actually surpass the original one just through algorithmic improvements, which would not be undertaken because of the concern of unsoundness in the original implementation. Okay, so it is reusing lean zone expert type. It's reusing a few algorithms when they are already available. It's really trying to be as similar as possible to the original lean kernel. One sort of unexpected benefit, which is what Matthew is hinting at here, is that people have been using this. So having a lean kernel instead of a C++ kernel means that people can sort of, lean meta hackers can sort of apply their expertise on this kernel in order to add, let's say, more logging or generating some SVGs or some visualizations. So that was sort of what David was working on. And Rishikesh has been working on an extension of this is some project to remove, like what would happen if you removed proof of relevance and sort of tried to patch up the proofs instead. If you had an axiomatic version of proof of relevance instead of a definitional version, could you somehow patch up the proofs? And so he did that through a kernel modification, which he's been experimenting a fork of this project. So here's some performance stats. So it's able to check things with about 20 to 40% slower than the original. And since the original is written in C++, I'm going to say that that's a win. Yeah, I think that we can do better. In part, we can do better when so there's a second compiler that's been under development for a couple of years now, and when it gets released, hopefully that these numbers will get even better, because I think a lot of this is just Lean's compiler needs to get better. And then other things I think we can get back with algorithmic improvements. Okay. Okay, yeah, so I want to now tell you about some of the properties in this sort of second part of the project. So the type judgment is undecidable. That is to say, the sort of idealized type judgment that would be closed under all of the operations which you'd like is undecidable. I won't go through the details of this proof, but yeah, you can construct some problem which sort of uses the accessibility relation in an inconsistent context in order to run something sort of in the wrong direction with a false proof of well-foundedness. And so if you sort of ask, like, okay, how does that actually work? Because Lean is actually doing something, right? Like, and the answer is roughly that Lean is under-approximating the definitional equality judgment, which means that sometimes it will say, no, two things are not definitionally equal, when in fact they are. It just isn't doing some crazy search in order to find out that actually they are. Yeah, in practice, this issue almost never comes up. It's actually surprising how little this issue comes up. There are other related issues that you could point at as, like, maybe this is related to why this is difficult, but Usually it's more like performance issues where, you know, a definitional equality takes a long time to check rather than it you know, running away or not being able to find some definitional equality. All right, so I want to tell you sort of major theorem here in lean. This is actually the largest theorem proved in my master's thesis, and it's called unique typing. The basic statement is that if you have a term that has two types, alpha and beta, then alpha and beta are definitionally equal. This is a really important structural feature of Lean's type theory, and the kernel uses it everywhere. It's very, very important. This is sort of proved in mutual recursion with these three theorems about how if you have a definitional equality of two universes, this can only happen if these two universe levels are the same. If you look at the kernel, it's going to have a sort of boring answer to this question. Like if you ask it, are these two universes definitionally equal? It will say, well, yes, I'll just check the indices. And like, sure, that's a very simple algorithm, but the correctness of that algorithm depends on this theorem. If it happened that somehow you could take UM and then turn it into a lambda and then turn that into something even bigger and then like reduce things here and there and then somehow come back at the end and you've got UN, then well, that would be a very weird system, but it would also mean that Lean is not implementing things correctly, right? So that's sort of, it's not a concern for the kernel, it's a concern for the proof. Okay. This exact statement is not true in Coq because of, or Rock because of universe cumulativity. So that is to say, if you have like the lowest universe and the second lowest universe, these two are not definitionally equal. But if you have an element of the lowest universe, it's also an element of the second lowest universe. But there is a version of this that can be stated involving principal types and such. It's a bit more complicated. Unfortunately, this is not actually a theorem. When I was in the process of formalizing this, I found that there was a gap in the proof. I will tell you a little bit about how it works. I still think that the theorems are true, but the formalization process has turned into an interesting mathematical problem. And so there are other alternative paths to the proof of soundness specifically, but a lot of the kernel does depend on this theory. And so the proof strategy that was done in the master's thesis was to do an induction on the number of all. So the challenge here is that the main part of the proof of unique typing that I'm going to describe depends on unique typing at the level of the types of the expression. So it's essentially, it's going to have some weird inductive structure to it. And there's some intuition that, like, if you look at the type of the type of the type of, etc. of an expression, eventually things sort of stabilize to, like, it's just type n. And so you're sort of grounded by the fact that, like, you don't have this crazy stuff happening at every level. But it's actually surprisingly difficult to sort of concretize that. So here the idea is we'll stratify the definitional equality judgment so that we have the number of alternate. So if you have a definitional equality, but then you use it in a proof of relevance proof, which requires typing, which can then use definitional equality again, you have this sort of back and forth between typing and definitional equality. So we'll sort of break that and have some stratification, and then try to prove it at that level. And so this goes via this Church-Rosser theorem. So in traditional lambda calculus, that says that if you have an expression and then it reduces to two things, then those two things can be brought back together. In Lean, this isn't exactly true because they won't be brought together precisely. They'll be brought together up to some equivalence relation. And so this is the version of the theorem that's actually used. So we have this additional relation here, which is a sort of almost equivalence. This is much stronger than definitional equality, and in particular, when you ask, is it the case that two universes have this property, then it's really obvious that they can only be, like, UN cannot be equal according to this relation to UN. And I will skip to the details. Oh yeah, so, but it turns out that this stratified judgment is not closed under substitution, and that's a problem for part of the proof. And so I think we just need a slightly smarter induction measure, maybe built in substitution into this rule. I don't think that this is a really difficult problem, but this is one of the situations where I would like to see it formalized before I actually believe. I went through like 9 bad proofs of this while I was writing this paper before coming up with this version. And so proof number 10 is also wrong. I want to have a formal version this time. Okay, but for part 3, I sort of decided to set this proof aside. Question?
There's no type of best approximation to substitution up to level 1 in this section?
I don't know what that would mean, actually.
I don't know what it means either.
It would be great if there was some. Well, I don't know. Is there such a thing as an approximation to substitution? I actually don't know. What I'm thinking more is you could have a version of this stratified judgment where you just say by fiat that like the substitution that it is closed under substitution. There would have to be additional caveats and so on. So there's a bunch of details, and every time you chase down something, it like pushes the proof work somewhere else and so on. So I'm sure that the people in this room are familiar with this sort of issue. Okay, so let me tell you about verifying the kernel bit. So Lean does not just implement this type theory sort of as is. It has a bunch of optimizations on top of the obvious definition in almost every single function. As a result, the verification is not at all straightforward. In order to keep the concern separate, the theory actually uses a different type of expressions than the real kernel. So this expert type uses locally nameless representation. That means that it has both deployment variables and also they call them free variables. So these are sort of variables with globally unique names. Expert has some additional primitives like natural number literals and string literals. These are morally just, compressed versions of 0 with a bunch of sucks on it. You just say 42 and you get the idea. It also has meta variables and these free variables. It also has primitive projections. These actually cause a lot of issues for us because primitive projections also have a sort of desugaring into an application of a recursor, but you can't actually write down what that desugaring is. Unlike the case of the natural number literal, you can't write the desugaring without knowing the type of the expression. So you need typing in order to perform this this translation. The expression also has some metadata. It has like, do I have a free variable inside every little sub-expression? And some of the functions on natural numbers, so if you do nat.add applied to 2 literals, it does not expand everything out into sucks, run the thing, and then put it back into a literal. Instead, it calls the GNU multi-precision arithmetic library in order to just do it directly. Well, or if it's a sufficiently small number, it will just do sort of machine addition. And so this is very important for being able to do like moderately large computations in Lean. This is a sea change actually in a lot of the mathematical work that has been done has really been enabled by this this shift from just using the core, having some functions called bit 0 and bit 1. That like it's okay, it's asymptotically equivalent, but it's still, we're talking 60x or more slower than just doing addition that your computer already knows how to do. Okay, so I want to show you a couple examples of what So I want to show you infer lambda is an example of this. Yeah, this looks a bit weird, but okay. So this is a function which is supposed to infer the type of lambda. This is actually one of the simpler functions in the lean kernel. And you think, okay, the lambda rule, it's not that complicated. You ask what the domain of the definition is, and then that's going to be and the result is like a pi type over that. And then you infer the type of the body. What it's doing instead is, well, it's not doing one lambda. It's doing a whole list of lambdas. So there's a loop right in here. It pulls off lambdas, and then it collects up some fvars, and it has some instantiation, and it does check the sort sometimes. There's an if statement here, because sometimes it doesn't know that it's well formed, and it wants to know the type and also check that it's well formed. Other times, it already knows that it's well formed. It just wants to know what the type is, so it wants to skip this step. So that's that's the function in lean for lean kernel, and then this is the sort of correctness statement for this function. Let's see. So here, there's our function infer lambda, and this is a kind of Hoare triple, although here we're just going to assume that we have the state. So this is a sort of technique in program verification where you have a sort of post condition on your on the result of running this function, and what this says is that if you run this thing and you get a value type, then E, our input, is well formed and translates into E prime, which is a, so if you look at the types here, E is an expr and E prime is a V expr. So this is the version of the expression that we're going to be working in our in the theory land. And our has type relation is only defined on V expr. So we need to sort of assert that things are well formed before we can make this statement. And then this is defined through, this is the inductive invariant for our loop function. And so there's a bunch of theorems like this. All right. So I just want to tell you a little story about how this project is starting to actually pay dividends. So just last week I was working on proving this. So when you, like, in order to prove that infer lambda, it called instantiate rev. Instantiate rev has an early exit when you don't have any bound variables in the expression. Then it doesn't. So it checks if the expression has any bound variables before it's going to substitute those bound variables. If it doesn't have any, then there's no need to recurse. So that's an optimization that it does. So in order for that optimization to be correct, we need to know that has bound variable does something smart. Has bound variable works by accessing this metadata field on an expression. This is a 64-bit value. So you'll have to prove some bit tricks correct. You know, this is starting to look very different from just, you know, proving properties about the type system. Now we're doing, you know, hardcore software engineering problems. But it works. So there's this BV decide thing that can actually solve these kind of bit problems. But I did find some issues. So the metadata calculates the depth of a bound variable. And the depth of a bound variable can be as large as you want in principle, right? It's a nat. But the value that it's going into is 64 bits. So clearly there's going to be some kind of overflow situation. And the code was checking for overflow. But it checks for overflow using the panic function. And the panic function doesn't actually crash the program, unlike what you might think. And I mean, in lean, it's actually really awkward if you want to, like, have some weird non-local exit because it's a pure functional programming. It doesn't have an exit path in this code. It just returns a 64-bit value, and that's it. So it's not allowed to have an error exit. So what does it do? Well, it returns the default value for the type, which is 0. And that's actually the worst possible answer you can give. That means that it has no bound variables, no free variables, so all of the optimizations apply. And it just makes a complete mess of the situation. And so by actually performing this proof, I end up with this unsolved goal. I sort of push it back to the entry point. I find like a concrete input that will get me to my counterexample, right? And so by doing this, I was actually able to construct a concrete proof of false. And so now this is sort of the first actual theory level problem in the kernel. So I submitted it as a PR to Lean 4, and they're working on it, and so it'll probably be fixed in the next version. And so for me, the takeaway, there's going to be bugs in any large enough piece of software, and there's going to be gaps in any large enough proof. I do not trust any authority on these claims, and not myself either. So that's why I'm formalizing the soundness proof and verifying the kernel algorithm. There are bugs here. We need to find them. Lean for Lean is really not an external checker. It copies the real kernel way too much for that. And in fact, the purpose is really the opposite. We want to make sure that if the Lean kernel has a bug, then the Lean for Lean kernel also has a bug, because the Lean for Lean kernel is the one that I can actually try to prove correct and find the bugs. So by finding bugs in Lean for Lean, I can fix bugs in Lean. Okay, so now I want to tell you about the second project. So I've been thinking about this since the summer, but only recently started actually writing some code for it. So I told you earlier that Lean is sort of equiconsistent with ZFC with there are n inaccessibles for every n. And so by compactness, every particular Lean proof has, it can be proved in ZFC with n inaccessibles for some particular n. Can we calculate what that n is, right? If you have a given Lean proof, can you ask how many n's does it need? And the answer is yes. So in 2021, I wrote a program that just counts up what's the highest n that's used in any occurrence of type n in MathLib. And so what's the answer? 4. Okay. Well, so every definition in theorem in MathLib can be done with at most 4 universes. But it's equally clear that this is actually a bad answer to the question, because I did not want the answer to be 4. I wanted the answer to be like 0 or 1. That would be much better of an answer. To give you an example of why, and I looked at the situations, like why is it, why am I getting type 4? It's not good stuff. It's really stupid stuff. So here's a even more simplified example where I'm doing nothing whatsoever, and somehow I'm getting these larger types. So the idea is I'm going to use, so id is the identity function. Here I have this 2 argument. I'm going to show explicitly the type because things happen here. So we're going to apply the identity function in a given type to an element of any type, and it just returns the value. So the natural numbers are the same as the identity function applied to the natural numbers. But in order to write this expression down, you also have to pass in the thing that n's type is. So n's type is type 0, right? So you would put type 0 in here. But you can also replace that type 0 with the identity function applied to type 0. And so you have to give the type of that, which is type 1. And so if you keep doing this, you just get larger and larger types. And like, okay, you're not doing anything. Like, what is this? So I mean, I observed this, but like that was sort of where the story stopped. This sort of unsatisfying situation. And so clearly, like those universes, they just need to be in a typing relation. They don't. This is way overkill. Like we're asking for it to be a Grothendieck universe, and all you're doing is just asking for it to have one element. Like what the heck? So where did this constraint come from anyway? So I went back to the proof of like the proof of soundness in the paper, and okay, how does it work? Well, so the construction of Lean model in ZFC. Sort of aware of this issue, and it builds on a sequence of strong limit cardinals, not inaccessibles. and it uses this predicate k correct in order to say that the first k are inaccessible. So this allows us to have a sort of relatively well-formed universe hierarchy, even though, you know, after a certain point, it maybe breaks down a little bit. And there are two cases where we actually need to assume this k correctness. Like, otherwise, we just have k equals 0 all the time, and then we wouldn't need universes. The two cases are the pi type and the w type. So the pi type, this is just, you know, dependent product. The w type is, in some sense, the universal inductive type. So you can take all of that inductive schema stuff, and then you can reduce it down to a small list of inductive types, and w is one of them. And so it's basically defined by this. So in set theory, you would say, okay, it's a small set which is closed under these two operations. Or sorry, that a pair is in W if A is in A, and F is a function into W. So because of this functionality condition, like here you're asking for W to basically live in a type which has high cofinality, and so you end up needing this property of inaccessible, that the universe is actually inaccessible in order to prove that it's closed under this operation. So if we could somehow reduce this list to just having W, that is to say, making sort of pi types cheap to have. You can just have as many pi types as you want, but W types, they're going to be restricted. Then we could maybe count up the W types, and we wouldn't have to worry about it. And the idea here is that, like, okay, Lean loves to use pi types everywhere, right? Like in all of these functions, you're using pi types in everything. But, you know, mathematicians don't use inductive types. They especially don't. Yeah, well, so they do use structures, but structures are like pairs. Like it's easy to handle structures. It's really the inductive types. And if you look at the construction of ZFC, it uses this type here, P set, which is a crazy inductive type. It's a W type that has a universe on the left. So this is an incredibly powerful construction. And we can be reasonably sure that this will not appear in any MATLAB or FLT or whatever unless it's actually necessary for the proof. This is just a very bizarre object to be talking about. But it's like, this is what you need in order to construct a model of ZFC. So like, okay, we'll just say, as long as you don't do that, like, you probably didn't use universes, right? So it turns out that eliminating pi types in the way I just described isn't possible. And the reason I know that is because I can actually construct the ZFC model without any inductives at all. And so there is a list of exceptions, which I have not been able to eliminate, but you can see that the list is very innocuous stuff, where we need subtype, we need an empty type, we need equality. This one I'm pretty sure we can eliminate. I'll tell you how we do it. And so I've been working on an actual formalization of this because I would love to have this done properly. So here's the blueprint. So for most of these types, true and or and so on, we can actually do it really easily because we have imperative props. So we can just say, like, if we want to do the equivalent of a inductive definition, we'll just say for all motives that we want to eliminate to, we just do this sort of thing. This is sort of copying the definition from the inductive type itself. And this only allows us to quantify over propositions, but in return for that, we can do these sort of constructions. And for a lot of the propositions, we can do this. We can do false as well with this method, but we don't get large elimination, and that's actually going to be important. We can get false, but then we won't get empty. So if we want to prove that there exist empty types, then we're going to need false. So okay, fine. We're going to actually take as axioms funx, propx, and choice. Now, funx, that is function extensionality, is usually not taken as an axiom in Lean because it can be derived from quotients. But actually here we can do it the other way around. So we'll prove quotients from funx. Excluded middle can be proved from choice. This is called the Diaconescu's theorem. And we're just going to go all in on classical logic, not even bother with bool. Prop is a two-element type, so great, we've got two-element types. We can define the accessibility relation, and this is useful to do well-founded recursion. So we can actually prove that well-founded recursion exists uniquely, and then we use the axiom of choice in order to turn this into a real function. So now we don't even have problems with large elimination. For the type formers, unfortunately, we can't quite do this, but we do have a sequence of constructions that get us most of them. So for p unit, we have this little trick here that gives us an element of one type, which is in the right universe. For u left, we have functions out of p unit. For empty, we just take an empty subtype because we're assuming we have subtypes. For lifting, you can do that. So once you have, well, with for all, you can use this in order to do binary products. I mean, it's a bit of, yeah. So the hard one is actually sigma. And this is the one which really, why I couldn't figure out how to eliminate subtypes, is because this construction really needs subtypes. So yeah, here you need to use pi types in order to encode sigmas, and you can do so with a function which is at exactly one point a constant function, and at everywhere else it's an identity function. So this basically eliminates all of the possible ways that it can move around except for having two values. And then using sigma, you can construct the binary product. Quotients, you just do the old school mathematics set quotients. And now we're going to do ordinal theory. So we need to, and actually this basically goes through the same as it does in MATLAB. So we define ordinals as the quotient of well-ordered types by equivalence. They're well-ordered by this relation of being a principal segment. And every type is well-ordered, so we can prove the well-ordering theorem. And then we can mimic, so this is the key part, we're going to mimic the cumulative hierarchy in order to construct our presets. So by well-founded induction on ordinals, we're going to define the LM type to be a sigma over sets of beta. So you can inline this inside that. So basically the idea is we're going to have we're going to apply the power set function recursively by induction over the ordinals. Okay, so by transfinite induction, we're going to apply power set over and over and over, and this is going to give us all of the sets that we need. And then you have to define what does it mean for two elements to be the same so that they will satisfy extensionality. And so you can do that just by defining subtype, subset in this way, equivalence in this way, and then elements, you're just getting the second component, and then these are all being defined by recursion, so that's why they're referring to each other.
Mario, don't you need the natural numbers to get the axiom of infinity?
Types, the universe is an infinite type. So by burning one extra universe, we're able to prove that there exists an infinite type. And so our final type of ZC sets is going to be this. And so this really shows that lean style MLTT, where we just take out all of the CIC stuff, just have plain pi types and really not much more, is already just as powerful as full lean inconsistency strength. So the status of this, I'm currently preparing this as a construction for MATLAB's counterexample library. And it's been really interesting, trying to use lean without any inductive types.
Volsky has a similar problem.
I mean, you still get a significant amount of benefit from lean, like having some of the notations and so on. Like you can actually build up a framework that you can work with well enough, but like most of, it's funny, you can use rewrite, but you can't use simp, because simp, at the very end, will close your goal by proving it's equivalent to true, and true is an inductive, which we've banned. Rewrite, however, only uses recursion on equality, which is an inductive type, which we've assumed. We could introduce our own equality, but then we wouldn't be able to use rewrite, so that would be sad. Yeah, so there's some syntactic things like, okay, you can't use .1 and .2 for and because it's not actually an inductive type. So yeah. Okay, so summary here. So for lean, you can use this as a replacement for lean's kernel today if you want. You can add it to your project if you want an extra double check on FLT or something like that. Formalization is still under active development. Not all of the mathematical problems are solved yet. And I'm looking for type theorists who are interested in collaborating on this project. I do not want this to be a one-person project, but right now it is. And yeah, there's a bunch more people working on Meadowrock, but Lean not so much, because I think there just aren't a lot of type theorists in the community. So hopefully people will look and see this. For this reverse Lean project, so I mean, I told you this negative result, so now the question is, okay, what are we actually gonna do? I think it is possible to track the sort of ranks of pi types, and I think you can still make it reasonably easy on most of what Lean is doing by you just assume some, like you have a cardinal which has some obscenely large cofinality, and then no one's ever gonna do anything beyond that. And then beyond that, you just count like how many times they've used, and then this construction here actually fail. Like here we're using the power set operation over transfinite induction. And it's like, okay, maybe that's a bit too many times. You're not allowed to use it that much. So ZFC has the ability to prove a lot of this stuff. So I think that there's still, basically the issues here are not around the tactic, they're around the theorem. So, what is the actual, given a Lean proof, you can prove that it lives inside some subset under some conditions. And the details of that theorem and the proof of that theorem are what haven't been worked out. Comparatively, it's relatively easy to write a tactic that will just walk over proof and check how many times did you use pi type in such and such a way. And so that will be relatively easy. And so this is a logician's wanted science. So thank you all for all.
So in the story with the type 4 appearing, so I do understand correctly that the way it actually happens in Mathlib is that some identity functions are inserted just to help the kernel, and this is really the example, the silly example that you showed is what is actually happening. So it's identity stuff showing up.
Yeah, I mean, it won't insert identities inside the types of identities in that way, but
okay.
Yeah.
So I have another question. So in the proof, I mean, you said you can use rewrite, but you cannot use simp. So, but how do you enforce that you are not using the tactics?
I can show you later, but there's I have a what is it? Print inductives.
Okay.
So I'm checking that it only has that list that I showed you.
Thank you, Mario. I was wondering what kind of extensions would you like to see to Lean type theory, if any? Of course, or maybe you are happy with the Carneiro shape. I don't know.
Extensions. Oh my. I would like to see reductions. I would like to see reductions more than extensions. I think that there's a lot of things that could be nested inductive types right now have a very messy implementation in the kernel, and I would like to have a version of that where we can simulate it without incurring the costs of simulate. Like it used to be a simulation, and then that was removed because it was too costly. And I think what they should have instead do is make that more efficient. Like figure out why it was costly and fix that instead.
Sorry, I don't know very much about meta programming, so I didn't answer the question. So you've got this proof that your lean specification executes on this specification, and then so that proof is itself being checked in the lean kernel.
Yeah.
But in principle, it could be checked in your lean for lean kernel.
Yeah. So
that would be like the kernel checking a proof of its own correctness.
Yeah, so
yeah. What does that mean? What does that mean in practice?
Yeah. So the main part of the proof here is that Lean's implementation, like the Lean kernel implementation, implements something consistent with the theory of lean, right? And so that, if you're thinking like, oh, I thought Gödel told me something about this, that's not actually a concern here because we're not actually proving that part of it is really just an implementation correctness thing. Now, in order to prove the soundness of like the other, that was also sort of on my to-do list, right? For that, you need to like construct a model of lean inside ZFC or something. And if you wanted to do a model of lean inside ZFC, you would need ZFC with omega universes. And I mentioned that lean can't actually prove the existence of ZFC with omega universes, just with everything less than omega universes. So you would need a little bit of extra hypothesis there. And so usually that's how these things turn out, is that you've got like an extra hypothesis in one spot or another saying, I need some large cardinal axiom, and then you can do the proof.
Can you, to what extent can you define like all the inductive types in your like smaller lean system to W pi types? Can you convert W types?
I haven't actually tried. Yeah. I mean, once you have the cumulative hierarchy, like you can do anything.
Yeah, I guess so.
Yeah.
This number 4 you had, how feasible is it to change the math of proofs to make it free?
Oh, I mean, it's relatively easy, but the issues, like, it doesn't change MATLAB in a way that we want, basically. So, like, I think that it's actually giving, I don't want to put that pressure on MATLAB. And I think that there's a way to do the math better so that the 4 is really a 0. That part, like, it's not, the definition of fin sum that we should be going after. It's, p set or ordinal or something that actually would, deserves to use universes.
So if you get 4 down to 0, that tells you that some theorem is provable in ZFC.
Mm-hmm.
What if you wanted to show that something's provable in some weaker system, like PA or something? Is there any way to do that?
I think that it's possible in principle. You would have to change some you would have to look at some different things. So I think the big thing there would be impredicativity. So if you could show that you weren't making use of impredicative prop so much, then you could argue that you're basically living in some subsystem of Agda, and then there things look very different. Although like lean uses impredicativity everywhere. So this is also sort of going after the pragmatic things. Like, I think it's reasonable to say like we aren't using universes. I don't think it's reasonable to say we aren't using impredicativity.
Okay, maybe let's answer the questions here and then let's thank Mario.